Welcome to Mickey Study Circle channel. In this video, we shall see how to perform the stress analysis of a stepped composite bar using the ANSYS workbench. Moving on to the problem statement, we have got a stepped composite bar which is having three components as shown in the figure, and each component is designated as AB, BC, and CD. And the geometrical parameters and the material properties pertaining to each of the section is given as below. So the AB is having a length of 800 mm and its cross-sectional area is 2400 mm square. Followed by the material property, that is the Young's modulus, it is 83 GPa. Next is the section BC. So the length is 600 mm and its cross-sectional area is 1200 mm square, followed by the Young's modulus, which is equal to 70 GPa. And next is the section CD of the composite bar, which is having a length of 400 mm and its cross-sectional area is 600 mm square, followed by the Young's modulus, which is 200 GPa. And this composite bar is subjected to the compressive loads P1 and P2 as shown in the figure, with the magnitude P1 being equal to 60 kilonewtons and P2 being equal to 75 kilonewtons. So assuming a Poisson's ratio of zero point 0.3 for all the three sections, so we need to perform the stress analysis, also determine the extension of the bar and the reaction forces at the support. So before we move on with the stress analysis using the ANSYS workbench, let us perform the calculations using the strength of material approach and arrive at the solutions. Moving on to the calculation of the reaction force, so we can just consider all the three sections of the composite bar, and each section taken individually we can write the reaction forces. So let the reaction force at the portion AB be designated as R of AB, and the reaction force at the other support, that is at the portion CD, be designated as RCD. So we need to compute the values of RAB and RCD. So considering the body to be in equilibrium, so since it is fixed at both the ends, that is at a statically indeterminate problem, so we'll tell that the elongation in the entire bar structure is equal to 0. So using this model, we'll write the mathematical model for the elongation in each section. And on solving, upon substitution of the values, we get the reaction force at the support AB section to be equal to 60.60 kilonewtons, followed by the reaction force at the section CD to be equal to 74 kilonewtons. So if we add up together, we need to get that equal in the magnitude of the applied force, but in the direction opposite to that of the applied force. So since here it is compressive in nature, the reaction force tends to be tensile in nature. Only then the body is said to be in equilibrium. Next, let us compute the deformation of each section. So we have got the parameters, that is the value of P, the value of the cross-sectional area, the Young's modulus. So using the mathematical model delta L is equal to PL by A into E. So all the parameters of deformation for all the three sections is computed as shown here. So the maximum deformation that we get to see is 0.2433 mm in the entire cross section, that is AB of the bar. And the minimum deformation that we get to see is in the extension, is in the CD, which is minus of 0.248 mm. So the summation of all this will be equal to 0. So now let us compute the values of the stresses. So the stress in the section AB is given by the mathematical model, which is nothing but the ratio of the force applied over the given cross-sectional area. So upon the substitution of the values of P and A, we get the result of stress to be equal to minus of 25.26 megapascals in the portion AB, followed by minus of 0.52 megapascals in the component BC, and also in the section CD we have got the stress value to be equal to 123.96 megapascals. So to sum up, the maximum stress in the structure is at the portion CD, which is equal to 123.96 megapascals. So with this, we have computed the values of the reaction forces of the supports, the total deformation in the bar, and also the elemental stresses. So now it is time for us to compute the same values using the ANSYS workbench. So let us see the steps that is involved in computing the values using the ANSYS workbench software. Since the problem statement is involving only the forces acting on a structural member, we shall consider the analysis system to be a static structural one. So double click on static structural and the project is going to open in the static structural mode. So first let us move on to entering the engineering data. So we have got three different materials as it is a composite bar. So we will just add all the three materials. So first is the material 1. So next we'll click to add the material 2, and next is the material 3. So we have defined three different materials. So it is time for us to assign the properties. So click on material 1 and select isotropic elasticity in the linear elastic. So here in this dialog box we'll be having different properties that could be defined. So for material 1, select material 1 and open the dialog box for linear elastic. Select isotropic elasticity. So double click on that and then you'll get a window to enter the values. So let us feed the values of the Young's modulus. So as per the problem statement, for the first component, the Young's modulus is 83 GPa. So we will enter that as 83 E3 megapascals, followed by the Poisson's ratio, which is zero point 0.3. So minimum of two parameters has to be entered for a new material. Similarly, select material 2, double click on isotropic elasticity. So as per the problem statement, the Young's modulus here is 70 GPa. So let me enter that in megapascals as 70 E3, followed by the Young's modulus, which is zero point 0.3. Similarly, repeat the same procedure for material 3. Select material 3, double click on isotropic elasticity. So let us feed the value of the Young's modulus, which is 200 E3 megapascals, followed by the Poisson's ratio, which is zero point 0.3. So now we have defined material 1, material 2, and then material 3 properties. So let us close the engineering data window and let us move on for creating the physical continuum using the geometry. So right click on geometry and select design modular geometry, and the progress could be seen here. So it is showing it is starting the design modeler, and now we have entered the design modeler mode. So select the XY plane and make it normal to the screen by clicking on this icon, that is look at face or plane or sketch. So click on this so that you get the selected plane as normal to the screen. So now by default, the interface is running on the meter and the degree mode. Let us change the units to millimeter as the physical continuum is defined using the millimeter dimension in the problem statement. So now let us go for creating the sketch. So let us start by creating a line. In the sketching mode, select line under the draw option, and then from the origin you can just see here point P appears here. So let me draw a line of any arbitrary length. So this is a line, horizontal line. Let me go for dimensions now. In general, select the line and it is asking the dimension. So as per the problem statement, the length of the AB section is 800 mm. So enter 800. Let us fit the sketch to the screen by clicking on zoom to fit or simply press F7 on the keyboard. So now you can just see that it is fit to the screen. So now the sketch 1 part is ready. So we need to create a new sketch for the next section of the composite bar. So after having done this, click generate and then go for new sketch option here. So click on this new sketch and then select the draw mode again, select line. So you can just see that the point P appears here. So draw a line, horizontal line, go for dimensions and select this line, which is H2. So let us change the dimension of H2 to the length of the second component, that is BC, which is equal to 600 mm. Again, let us use fit to screen. So this is how we create the second section of the composite bar. So click on generate, go for new sketch. So sketch 3 is there. Click on draw, select line, and from here let me draw a horizontal line. Go for dimensions, select general, and then assign the value for H3, which is equal to 400 mm as given in the problem statement. Click enter and then fit the sketch to the screen and then click on generate. So now we can just see that we have got three new sketches: sketch 1, sketch 2, and sketch 3, which represents the three different uh, cross sections or the sections of the composite bar. So now let us go for concept and select lines from sketches, which is important for us to create a body. So select line 1. For line 1, select sketch 1. So you can see that it is selected by default. And ensure it is add material for the first section. Click on apply and then select generate. So the moment you click generate, 0 part 0 body converted to 1 part 1 body. Correct? So now similarly, we'll go for concept, select lines from sketches, select sketch 2, and then here instead of add material, select add frozen, so that it builds a connectivity between this section and this section. So reselect sketch 2 and click apply and click generate. So you can just see that it is line body 1 and line body 2 is created. Now let us go for concept again, select lines from sketches. So select this line or the sketch 3, and then here also select add frozen and click apply, click generate. So you can just see that line 1, line 2 is created from the sketch. So that is why I've used create line from sketches. So remember the procedure. First we have created the sketch and then we have created a line using the sketch that we have created. So now we need to assign the cross-sectional area for each of the line that is created. So for that, let us go for concept, select cross-section, select rectangular. So here it is important for us to assign the dimensions. So he tells that the first section is having a cross-sectional area of 2400 mm square. So we need to assign the values of B and H in such a way that the product of B and H, because that is the area of the rectangle, that is length into breadth or breadth into height in this case. So that area should be equal to 2400. So that is our necessity. So we can take any combinations of B and H, which is going to yield the product as 2400 mm square. So here, let me take the base as 80 mm and the height as 30, or I can interchange 30 is the base and 80 is the height. So I'll consider this way. Uh, Anything is fine. So just click on generate. So rectangle 1 is defined. So next go for concept, select cross section, select rectangle. So the second section is having a cross sectional area of 1200 mm square. So here also again I can take the combinations of any two numbers that is going to yield me the final result as 1200. So let me take the combinations of say uh, 30 and then 40. So 40 into 30 is 1200 mm square. So click generate, go for concept, select cross section, select rectangular. So the final component is having a cross sectional area of 600 mm square. So let me take it as 30 cross 20. So the product is 600. Click generate. So now select line body 1, select the cross sectional area and select rectangle 1 as the cross section. Then click generate. Select line body 2, select the cross sectional area, select it as rectangle 2, click generate. Select line body 3, so you can just see that the yellow part highlights the component which is selected. Select rectangle 3 and click generate. So now we can just go for the view option and select cross section solids. So you can just see that how the composite bar is defined in terms of its thickness, that is the 3D component could be seen like this, correct? So this is the stepped bar that we have created. So now each of this is a single different entity. So you can just see that line body 1, line body 2 and line body 3. So for us to make it a single component, what we need to do is we need to select all the three line bodies. So using the control key on the keyboard, select all the three components, right click and select form new part. So this part is a single entity now. So you can just see that the moment I click on part in the tree outline, the yellow line is showing all the three sections. So which tells that the entire entity is considered to be one single bar, right? So that is the important step here. So after having defined the line bodies, we need to ensure that it is considered to be one single part. So with this, we complete the creation of the physical continuum using the design modeler. So in the next step, let us go for meshing and then applying the boundary conditions and the loads. So let us close the design modeler component. Let us go for the model component now. So double click on the model. So it is showing here starting mechanical. So this shows the progress. So we require some time for the modeler to open. So by default, it will import the previously generated model from the geometry. And you can just wait for that to happen. So now you can just see that the model is imported and it is being shown as a single line here. So here it is again in metric mm. So this is the units. So now let us just go for display and select thick shells and beams and cross section. So you can just see that the component is being shown in a complete beam structure with its cross section on. Correct. So this is the composite bar that we have created. So now it is time for us to assign the material for each of the component that is created. So go for geometry and open up part and select line body 1. So by default, the assigned material is structural steel. So click on this, and for the first component, apply material 1. Similarly, select line body 2. Select structural steel, which is by default, and assign material 2. Select line body 3 and assign the material as material 3. So with this, we have assigned each component the material. So in the ANSYS APDL, we generally do this procedure in the mesh attributes, but here, this is the procedure followed. So now let us close the part in the tree outline. So you can just go for the materials. So you can just see that material 1, 2, 3 is defined. So now it is time for us to discretize the continuum. So right click on mesh and select generate mesh. So it will take some time to create a mesh, and you can just see the discretized model. So this is the FE model. So now we need to apply the boundary conditions and the loads as given in the problem statement. So let us go for static structural. So the moment I click static structural, you can just see that the menu is going to change here. So get to environment and select fixed and select the vertex mode, or you can use Control plus P. So it is the vertex of the point. So select this option. And so this end of the bar is fixed. So select this end and select apply. So you can just see that this is applied as a fixed support. This end is applied as a fixed support. So again, select on fixed and select this vertex and click apply. So you can just see that it is fixed. So whatever parameters we apply in the tree outline, you can just cross check. So the green tick indicates that it is completely defined. So fixed support 1, fixed support 2. So now we need to go for applying the loads. So let us see how the loads are applied. So in the problem statement, you can just see that the loads are acting at this point, that is at B and C, that is P1 and P2, and P1 being equal to 60 kilonewton and P2 being equal to 75 kilonewton. So now let us go for applying the loads. So here there is something called as force. So select the force component and define by select it as components, and all the forces are in the x direction but in the negative. So minus of 60,000 newtons, that is 60 kilonewtons. So it is asking where to apply. So apply it here. So that is the condition. So this is the first load that is applied. Again, select force. So define by component. And then we'll assign the direction as minus of 75,000 kilonewtons, which is 75,000 newtons. So press enter and ensure it is in the vertex mode and select this point. Click apply. So you can just see that the force is applied here. So in order to check, click on fixed support. You get to see this, it is applied. Support 2 is here. Force 1 is acting here. The magnitude is 60,000 newtons minus 60,000 component. So force 2 is minus 75,000, comma 0, comma 0. So this is how you can just check in the tabular data as well as here in the screen. So this is how we enter the boundary conditions and the loads. So now it is time for us to solve. So go for solution and then right click and select solve. So it will take some time to solve the mathematical model, and the green tick indicates the solution is ready. So let us go extract the results. So right click on solution now and select insert and go for probe and select the force reaction. So select at fixed support 1, right click and tell retrieve this result. So you can just see that it is in the direction opposite to the applied force and its magnitude is equal to 60,624 newtons, which could be recorded here. Similarly, go for solution, select insert and select probe and select force reaction, select fixed support. So you get to see that fixed support is represented here in the tree outline. Select retrieve this results. So you can just see that at this support the reaction force in this direction, so which is exactly opposite to the applied load, and its magnitude is equal to 74,376 newton. So if you add up both the forces, it will be equal to 60 plus 75 kilonewtons in the direction opposite to that. So the first parameter is evaluated. So now let us go for solution. Select insert and select deformation, probe deformation, and select evaluate all results. Or this deformation you can fetch it from here also. Select total deformation. Let us just delete this component. So select deformation here and select retrieve this result. So the deformation, you can just see that 0 is the minimum deformation and the maximum is 2.479. E5 is the maximum deformation. So here in this section, the red component. Okay. So next is the solution. So click on solution, go for stress or in the beam tool. So select solution, insert, select beam tool and click on beam tool and select evaluate all results. Open the beam tool and select direct stress. So in the theoretical calculation, we got to see that 123.96 is the maximum stress in this portion of the bar, and the minimum stress was minus of 25.26, so which is in the blue region, and the red region represents the maximum stress that is distributed within the bar. Right. So with this, we complete the computation of all the three parameters. So it is now time for us to extract the results. So let us go for ohm and select uh, the print preview. So go for okay. So we can just go for images and save it as image to file, or else we can just go for a report preview, and then the report is generated by default. So this is the model that is created, and these are all the parameters that we have defined. So by default, the report could be extracted. So with all the results and the parameters that we have defined. So this is one way of generating the report. So this is the loads that is applied. And then we get to see the other parameters. So this is about the report generation in the ANSYS Workbench. Then we can just go for print preview and select the parameters here, direct stress. So direct stress, this is the results that we get. So direct stress with the legend. So right click on this and then you can just save the picture as JPEG. That is one thing. Or you can directly give it as print and take a print of this result. And the next option is you can select the dimensions to be in mm or anything. The stress is shown here in megapascals, as you can see here. And next, if you want to check the minimum combined stress, the maximum combined stress, all these parameters. So this is the reaction force, and this is the force reaction too. So for all the parameters that is to be presented in the report, you can just click on this using the print preview and save each of them as the save picture as a JPEG file. So this is the total deformation. So this is how we create the uh, print preview and take the print of the parameters that is being defined. So with this, we have completed the video, which details us about the stress analysis of a composite bar using the ANSYS workbench, and also we have done the comparison with the analytical approach. Thank you all for watching the video.